Okay, it's 12:30, so let's get going here. Assignment number 4 is due on Friday at noon, and today we will begin talking about R, and this will be the last main topic of this course. Are there any questions before we begin? Okay, so let's start talking about R. So R is really, well, first of all, R is a statistical software package that's available for free, in case you're not aware of this already. And it really has revolutionized statistics. In my 20 or so years that I've been a statistician, this has been, I think, by far the number one thing that has changed practice. You know, when I was a student, as I've kind of said before, you know, pretty much every department of statistics had students do everything, all the statistical computations of known statistical methods, had them do it in SAS. So of the courses that I actually had to use a computer for, all of them except for 2 when I was in grad school use SAS. The 2 that did not use SAS use a software package called S+. It's important to know here in the history of R here. So let's talk about how R came about. You can trace the roots of R all the way back to the 1970s when AT&T Bell Labs developed a programming language. I'm not calling it a software package, but a programming language like C or Fortran, which they called S for statistics. The main guy who was behind this was someone by the name of John Chambers, and he actually won a prestigious computing award for his work on it. And John Chambers is still alive. There's a really interesting interview of him that lasts for about 10-15 minutes, I think. It's on YouTube at that address if you're interested. It was just recorded about 2 years ago, I think. So S was developed by AT&T Bell Labs, and they made it freely available to others who wanted to use it. And a company picked up on this in the 1980s and decided to add some functionality to S. And so they developed an actual software package that used S called S+. Then in the, and one of the key things was that they started selling it to people. So S+ wasn't free, S was free. And then eventually the company that owned S+, got exclusive license from AT&T Bell Labs for S, so people couldn't get S for free anymore. This was in the early 1990s. Then in the mid-1990s, 2 New Zealand-based researchers, and notice that the first letter of their names begins with R, decided to develop their own statistical software package based upon the language of S. And so they often said their language was not unlike S. It could be, well, it basically was essentially the S language, but with improvements. Interestingly, software companies cannot, I guess it would be copyright, cannot actually copyright their syntax that they have for like a programming language. And so, even though some company owned the exclusive rights to S, they can't necessarily copyright the exact syntax. In fact, SAS has engaged in legal battles with companies that have actually tried to basically come up with their own version of SAS. It's not exactly the same, but basically using a programming environment that had the same syntax. And SAS has lost court cases. In particular, there's a company in the UK which sells a much cheaper version of SAS, you could say, that upset the company SAS. And so anyway, so these 2 researchers in the mid-1990s started developing what eventually became R. In 1996, I was a second or third year grad student at the time. They published a paper on their new software package. I actually subscribed to this journal that they published in, but I didn't take note at the time, or didn't even pay attention to the fact that this new thing called R is becoming available. And it wasn't until February 29th, so I guess you could say the leap day of 2000, that a full-blown version of R was released to the public. So before that, it was just in beta test versions. And I first started hearing about R in 2001. So, it's really, in the grand scheme of things, not that old, despite having roots back to the 1970s. I first, let's see now. So I first started using it in my classes in 2002. I taught my first class with just R alone in 2004. So before that, I was teaching basically everything in SAS. Some other interesting historical notes that occurred. So in 2004, there was a very interesting set of presentations at the joint statistical meetings. This is like the biggest gathering of statisticians in the world. So last year, for example, we had 7,000 people meet up in Chicago for these meetings. But in 2004, an SPSS executive, so SPSS is a commonly used statistical software package by people in the social sciences. He gave a presentation in this standing room only session where he said, these statistical software companies are starting to feel the impact of R. That we had this first freely available, fully functional statistical software package out there, and that's cutting into their sales. And so they're going to have to change their model, their business model some. In 2007, a company by the name of Revolution Analytics was founded, which started selling R. They might be wondering, well, wait a second. Why would anybody buy R if R is free? Well, what they decided to do, it's an interesting business strategy, was that they did add some stuff to R, in particular for those people who were interested in big data and parallel processing. They added some functionality components. They also added a nice programming editing environment. But most importantly is that, for companies to start using this free software package, there was one hurdle to overcome, and that is, or at least at the time, and that was, who are you going to call when it breaks down? Well, R was a freely available software package put together by researchers. And so there wasn't like a company that you could say, hey, my R is not working, or I can't get R installed on my server. I need help. And so what Revolution Analytics then provided was that help. And now there's a few other companies that are like that as well. And I think a big thing that happened fairly recently that just shows the impact that Revolution Analytics has had is that Microsoft actually purchased them in 2015. Also, a little bit of a side note, one of the founders of SPSS actually was the CEO of Revolution Analytics for a number of years, too. In 2008, again, this was at JSM, I attended a presentation where the editor for the Journal of the American Statistical Association, which is like the top or second best statistical journal out there, he actually says that R has become the de facto statistical software package for researchers. Meaning that if you're doing statistical research, now I'm not saying applying a known statistical method to solve a problem. I'm talking about actually developing new statistical methods. That's what that journal would publish. Almost everyone uses R. Now before that, that wasn't the case. Or a number of years before that. Like when I was in grad school. Some people even still would use SAS back then. Very little people use SAS now for statistical research. Some people would use MATLAB. Some people would use, a lot of people use like C to do stuff. Still, some people do, yes. But this has been a big advancement because now statisticians speak the same language, you could say. So rather than not being able to implement a method because, oh, I don't know how to use that statistical software package or I don't know how to use that programming language, we all use R now. So it's been a big advancement. Another reason why, too, that statistical researchers, almost all of them tend to use R for their research is because R actually provides a very nice way to disseminate your research to others. We've seen CTAN, the Comprehensive Tech Archive Network. Well, today we're going to look at the Comprehensive R Archive Network, or CRAN. And what that CRAN does, it allows researchers essentially to upload their programs, their functions that they're developing in R, upload it to the server, and then anybody can access it, essentially. And it's all free. A big turning point in the R revolution was then when the New York Times actually had an article about R and how it's just, and how fast its use is growing. And I highly recommend that you take a look at that article. There's an R journal out there. In terms of versions, we're in 3.3 or so. And in 2015, the R Consortium was founded. So previously, the main thing that supported R was a nonprofit organization called the R Foundation. And basically what this did was provided a way for, let's say, people to donate money to the development of R, and also provided a little bit of a governing structure to this freely available software package that doesn't really have a company behind it. And so the R Consortium was founded that contained the R Foundation, but also a few companies that are really, really wanting to forward the development of R, including Microsoft and some other companies that were like Revolution Analytics, and there's a few other companies involved too. And so, I mean, R is still going to remain completely free, but and this happens with other computing-related products, is that there are companies that are okay with the fact that it's free, but they want to help to forward its development. Okay, so enough about the history of R. I will not ask you a question directly on the history of R, except for maybe it might be an extra credit problem on the test. So let's talk about how to install R. So again, there's CRAN, Comprehensive R Archive Network. This contains, first of all, the main distribution of R itself. And so if you click on that web link there, it will take you to this web page here. And simply all you do, and I'm just going to talk about the Windows version because that's the main one I use. You just simply click on this. You get an executable file that's downloaded to your computer. You get 2 versions of R installed. You get a 32-bit version, and you get a 64-bit version. I don't know how much longer they'll still have 32-bit versions, but they've been doing it for a number of years now. So let's talk about the basics of using R. So you'll get and if you just go with all the defaults for installing R, you'll be fine. You'll get a little R icon on your desktop, and when you click on it, you'll open it up and look something like this. I'm using here R version 3.2.2, which I guess a little bit older, but it will be fine. So when you start R, this is what you get. So if you notice, you have this window here in the middle. This is called the R console. This is where you can type commands. R is a lot more interactive than what you would have with SAS. So at the bottom here, you see this little greater than sign. That corresponds to the command prompt. And at this command prompt, you can simply use it like a calculator, such as 2 plus 2, and notice R brings back to you 4. Now you might be wondering, why do you have that bracket 1 and bracket right next to it? Well, basically, ours is treating this as you have a vector of values that are returning to you. The first element of that vector is 4. So that's why you see a 1 there. It's not that important, but sometimes you might wonder, why do I have a 1 there? If you had something returned to you that had, let's say, more than one element to it, and maybe extended down to another line, then you might see a 1, and then you have all these values that you calculated, and then in the next line, maybe you have 9, meaning the 9th element is now the first part of that second line. So I can do, let's say, 2 caret sign 2, which means 2 raised to the 2 power. I get 4 as well. And also I can do stuff like this. P norm 1.96. And put that in parentheses. And what this does, calculates a probability value from a normal distribution, standard normal in this case. What's the probability that you're to the left of 1.96? It's 0.975. I could do Q norm, or Q norm parentheses 0.975. And what that's going to give me is my quantile back. What's a 0.975 quantile from a standard normal distribution? You can also do logical comparisons, such as, say, 1 is 1 greater than 2, so 1 greater than sign 2, false. How about 1 less than 2? True. All right. How about 1 equal 1? Syntax error. Can't just use a simple equal sign. You need to actually use a double equal sign. You'll see why that equal sign means something in R or is used in other places. So that's why you can't just use a single equal sign. Now, there might be times when you would like to actually be able to, let's say, save the results from a calculation that you did in R. And what that means in R's terminology is that you want to put, let's say, the results from 2 plus 2 into an object. So I'm going to save the results of 2 plus 2 in an object. And the way that I'm going to do that is as follows. So if you notice on the right-hand side there, I have 2 plus 2. And then you see a less than dash. If you put that together, it looks like a left arrow. In other words, I'm going to take 2 plus 2, and I'm going to put it into what's called an object, and I decided to call that object save, for the lack of a better name. So when I hit enter, notice what happens. You don't see the results of 2 plus 2 coming back to you anymore. Why? Because it's in save. So if I type save, there you see the 4. So that less than dash, the way that that is actually read, when you actually, let's say, verbalize R code, when you're speaking R code to somebody, because I'm sure you all will want to do that at some point, the way that that's verbalized is that somebody will say on this line of code here, save gets, G-E-T-S, the results from 2 plus 2. So that less than dash is verbalized as the word gets, G-E-T-S. Now, 1 could do something like this. I guess this is one example of where the equal sign comes in. And you'll get exactly the same result. So you might be wondering, well, why am I doing 2 keystrokes instead of just the simple 1 keystroke of the equal sign? Because that makes sense, because so many other languages use an equal sign. Well, there's a number of reasons. The main one is, I guess, all advanced R programmers, except for one that I know of, always uses less than dash, because that's what was originally available first. The equal sign could not be used with this until about the year 2007 or 2008. So there's a history behind why people use less than dash. And this is just the most common way that people approach this. If you use an equal in your code, people might laugh at you. So if you do that, and if you want to amuse me when I'm grading your homework, put an equal sign there. It's supposed to be kind of a joke. Anyway, sometimes talking about coding, it can be quite dry, and so I try to put jokes in there sometimes. But seriously, less than dash. That's what's used most often by far in practice. If I see somebody using an equal sign, I usually think, okay, they don't really understand how to use R. Just a little bit of a side note, too. So let's say if I wanted to combine two words together to be more descriptive of this object, I could use save underscore it gets 2 plus 2. Or what's more commonly done is to put a period in there. Save period it gets the results from 2 plus 2. And people usually verbalize this as save dot it rather than save period it. Most people don't use the underscore, and the reason being is because in S and also in earlier versions of R, the underscore actually meant the same thing as the less than dash sign. So when I was first using S plus as a student, I always used the underscore, and then when I was early on when I was a faculty member, I always used the underscore, and then R dropped the underscore, so I had to change all my code of any program that I ever had created in this syntax here. Now, this save.it, any of these objects I've created, they are in R's working database, you could say, similar to the work library in SAS. Now, to see the working database that's available to you, and to actually see like save actually listed there, we can use what's called an R function called ls parentheses and parentheses, and you can see it there. You can also do the function objects as well. So let me just back up a second here. So this p norm here, it's actually in R's terminology a function. And you're evaluating that function at 1.96. Q norm is a function. You're evaluating the function at 0.975. LS is a function as well, but I'm not using any options, you could say, with the function. So that's why I just had a parenthesis there without anything inside of it. If I ever wanted to remove an object, you could use RM. And there we go. For those of you who have any Linux experience, you'll note that ls is a function that you can use with Linux. RM is a function you can use with Linux as well. And you'll see this in many different versions of R syntax, that you see some corresponding coding conventions as what's done in Linux. Okay, any questions so far? Okay, let's talk about writing our own function. Let's say that I want to write a function that calculates a function that can be used to calculate a standard deviation. So I guess just to make sure this is clear, calculations that you're going to be doing in R are based upon using functions, kind of like procs in SAS, but into a lot more general sense. I guess the closest similarity to SAS is using a macro to some respect. So let's say I want to actually create a function that calculates the standard deviation. Now there's already a function that does that in R. It's called SD. But let's say I want to create my own. I'm going to call it SD2. Now the first thing I need to do to calculate a standard deviation is I need to have some data that's available to me so I can calculate standard deviation on that data. So I'm going to create I'm going to create an object in R called X, and that's going to contain my data. And simply what I'm going to do is I'm going to combine together the numbers 1, 2, 3, 4, 5 into a single, we can call it a data set. In R's terminology, this is actually going to be a vector. That C there, right there, stands for combine or concatenate. I'm bringing together these numbers into a single vector in R's terminology. And so when I hit enter there, and if I type X, you can see it. Okay, so that's my data set. Now to create this function, I first give it a name, SD2. So SD2 gets function. And now I need to somehow specify, I want to pass information to this function for which I want to calculate the standard deviation of. And so I'm going to create what's called a, the name's escaping me right now, an argument. I want to create what R calls an argument that's going to allow me to contain this data that I'm going to pass into it. For the lack of a better name, I'm going to call this argument numbers. So SD2 gets, it's going to be a function with one argument called numbers. And then to start, let's say, the main body of the function, I use a left bracket, and then I hit enter. Notice what R returns to me. Not the usual command prompt, but a plus sign and says, meaning, give me more information. You need to add information here. And simply, how can I calculate a standard deviation? I'm going to do it really simply. I'm going to take the square root of the variance. So how do we calculate a variance? Var, and I'm going to calculate the variance of the information that's in numbers. And also, I want to take the square root of it. So I'm going to take the square root of it. So SQRT is a function that does square roots. Var is a function that does variances. I'm going to hit enter. And then it says, okay, I need more information. Well, actually, I'm done. So I can end the body of the function with the right bracket. And now I'm back to a regular command prompt. SD2 is a function, but in R's general terminology, this is also an object. So notice if I do ls, you can see SD2 sitting there in that working database. So if I did SD2 parentheses, now remember we had an argument called numbers. Well, I need to somehow relate what was an X to numbers. And all I need to do is just simply put X now in that parentheses. So that when I hit enter, there's my standard deviation. Quite simple. Now let's check it. Again, there's a function called SD already, and I get the same result back. If I wanted to, I could have saved the standard deviation in object. SD, so I could do save.sd gets the results from SD2. And notice nothing returns to my screen. But if I do save.sd, there you see it. Let's do a little bit, let's change the function a little bit here in terms of the actual, the code inside of it to illustrate some things. So I'm going to create the function again, SD2 gets function. The first thing I'm going to do is now this time I'm going to, and this is in the notes, I'm going to save the results from calculating that variance into an object called y. This y itself is only going to exist inside the function. That's it. Hit enter. And then I'm going to do sqrt y. So now I just have a two-line function in terms of its body of the function. So as you might expect, this is still going to work. But the reason why I'm showing you this is that, notice, we don't know what y is. That information wasn't returned to us. Only that standard deviation was actually returned to us. Well, y, as in WHY. Well, the reason is because what R always returns to the user, this is very important, what R always returns to the user whenever a function is actually run, is what's in that last line. Only that. Well, maybe for some reason you still wanted that, what the value of y was. Well, what could you do? Well, let's rewrite the function. Okay, so I rewrote that function, and again, y gets the results from numbers, and then I combine together, similar to how you're combining 1, 2, 3, 4, 5 together, the square root of y, and again what R would call a vector. So that when I run this function now, I get both things returned to me. Again, whatever is in that last line is what's returned to the user when you run a function. Very important. Now you might have saw me here write this code rather quickly. And this is something that's done in Linux too. If you hit the up arrow key, you can cycle through your previous commands that you just typed. If you do the down arrow key, I can go back the opposite direction of the commands that I have typed as well. And so that's a quick way to bring back up commands that you have already typed. Let's do one more example here. Just a second. Just to save time, I'm copying and pasting the function that I was going to retype from where I have it actually stored in a program, which we'll talk about later. And so this is the same, essentially the same function that we wrote before. The only difference is that notice how I have this cat function there. Again, cat comes from Linux. It's a way to print stuff to your screen. So what I'm going to do is inside the function, when the function's run, I'm going to have R print the data. That /n is just a little bit of a Linux shortcut to mean go down to the next line, and then comma numbers, meaning whatever number is going to be printed, and then comma, go down one more line. So if I run this, we have the data printed. So maybe there is some other results that you want printed to the screen. You don't care about saving them. Well, the cat function gives you one way, where you can put stuff inside that cat function, separate the different elements by commas. There's also a print function as well that I could have used in a similar way in this setting. Are there any questions? Yes.
So R treat everything as float type. I mean, if you calculate 1 divided by 2.
Yeah, you don't have to worry about it being integer. You don't have to worry about it. Like I know at least earlier versions of Python. If you did 1 divided by 2, it wouldn't like it, or maybe it would give it a value of 0 rather than 0.5. R is also case sensitive, so a capital S is different from a lowercase s, which is different from SAS. Okay, so let's say that you need some help. Let's say you can't figure something out in R. What should you do? Should you contact me immediately? No. Instead, what you should do is look in the help that comes with R first. So if I come up here to help, you're going to see a variety of different options. For example, there's a whole bunch of manuals that are all in PDF form available to you. We're going to look at this HTML help. And you actually have access to the manuals here as well. We're going to focus on the reference section. So they have a nice little search engine. So if you want to search something, you could do that. Instead, we're going to look at this packages. So if you remember how SAS is organized into different components. There's base SAS, there's SAS stat, there's SAS graph, there's SAS QC, there's SAS OR, there's SAS a lot out there. Well, R is organized into packages. And these packages are basically, each package is a combination of functions, and some will also have various data sets in them to help illustrate certain things. So functions and data sets combined together form a package. Now I'm going to come down to the bottom here. With the default installation of R, you have a number of packages that come with it. So base. Well, we've seen base SAS. So as you might expect here, this base package for R contains a lot of the basics of what you need to do stuff in R. There's also one called stats as well. So I'm going to click on stats, and let's look up the help for that p-norm function that we used earlier to calculate a probability from the normal distribution. So I click on P, and there's p-norm. There it is. And up we have come up a little help web page. This is on your computer. This is not out on the web, even though you're in a browser here. You have the corresponding help of how to use p-norm. Now, as you might expect with various software packages, it's not necessarily straightforward to understand exactly what's actually being given to you here in the help. So let's talk about all this here. So a description. This does various things with the normal distribution. Here we have under usage p-norm. This is the actual syntax for how to use it. But we also have a number of other functions associated with normal. And so what they decided to do was just kind of combine this all together in one place. So d-norm stands for density normal distribution, so like your f of x quantity. P-norm, probability normal distribution. Q-norm, quantile from a normal distribution. And R-norm, what do you think that is? R standing for random. So I want to randomly simulate data from a normal distribution. Now we have these arguments. So if you notice here in parentheses, if we again focus on p-norm, you see some things listed there. This is the formal arguments that are available to you, or you can say options. That's not the common term that's used, but it's an easy way to explain this. Various options that you can use when using this particular function. So for example, you see p-norm q. Quantiles. So when we actually ran p-norm before, we put 1.96 there. 1.96 was a quantile. What was returned was the corresponding probability. Again, 0.975 quantile from a normal distribution is 1.96. Now, in that syntax, you saw Q listed. Well, this shows you how else you could actually get the same results. I could say p-norm, parentheses, Q equal 1.96. Notice how the equal sign is used there. That's the main reason why you can't do something like this, 1 equal 2. Because of how that equal sign is used in that kind of a location. In addition to now, using equal as mean less than dash. At least this was the original reason why you could just do 1 equal 2 and you would need a double equal. So anyway, so p-norm q equal 1.96. Also in this help, get rid of some stuff here that I don't need anymore. You see mean equals 0, SD equal 1. So those mean and SD are two additional arguments or options that you can use when using the p-norm function. Since they have numerical values or values after any kind of value after the equal sign there, that means these are the default values. So if I come back here to my code, and run it like that, I get exactly the same results because I'm just using what the defaults are. Do note that, notice how I'm putting spaces there between or around that equal sign. You don't need to do that. It will work fine if you don't put the spaces there. That's not something that's needed in the code. I just do that because it looks nicer. But also, this allows you, since you can actually include the argument names, unlike other software packages out there, you can change the ordering of stuff. So now I put SD first, mean second. same exact values as before, but I can change the ordering. So that's quite convenient because now you don't need to remember, okay, which comes first, the quantile, the mean, or standard deviation. It doesn't matter. So I strongly, strongly recommend to you that you always try to include the argument name there to prevent possible mistakes that could occur. Also, it makes your code much, much easier to read if you include the argument names. Whenever I do my coding, as you will see, I always include the argument names unless it's an extremely simple function where it's obvious what this is. Usually functions that maybe only have one argument to begin with. So always try to include the argument names. It will make your coding a lot better. Now, you'll also notice here in the syntax, so it said Q, vector of quantiles. So one of the cool things about using R, and this is done on purpose to help make coding easier for people, is that R tries to have its functions operate on vectors of information. So we talked about the C function before. I used that terminology, that C function, to create a vector of data. Well, notice here, I could find the corresponding probability for both negative 1.96 and positive 1.96 at the same time. So that negative 1.96 and 1.96 is a vector. So I don't need to do them separately. I can do it all at once. You might be thinking, oh, okay, big deal. This can greatly simplify your code, especially if you've had a programming language like C or Fortran or some other of those lower level programming languages. You might be thinking, oh, I always have to do some kind of looping structure if I want to do the calculation for more than one thing. In R, you don't often, because of that ability of functions to work on vectors like that. More on that as we go along with our discussion this semester. Now, if we keep on looking through this help here, you have all the arguments. You always will have a detailed section that explains the actual computational details. It will tell you, well, what kind of value is actually returned to you. It will give you some nice references and stuff. And always at the bottom, you have some examples. So you can actually copy and paste this directly into R and run the example. And that's a great way to learn exactly how something is done. Okay. Are there any questions? So we are on page 10 now. So what I would like to do next is do a simple example that involves finding a confidence interval for population mean using that standard t-distribution based formula. Excuse me. Can I get to that place in the notes? So again, that formula is, let's say my sample mean is going to be x bar plus or minus the 1 minus alpha divided by 2 quantile with n minus 1 degrees of freedom from a t-distribution, excuse me, times the sample standard deviation times the square root of the sample size. Okay? That's the standard formula there. And so the first thing that I need is some data. I'll explain what this thing is up here that you see. Maybe not today, but next time definitely. So there's my data that I'm going to use. A small sample. Let's see, a sample size 4, 5, 6, 7, 8, 9, 10. And so if I type X, there's my sample. So, how would you expect that I calculate a sample mean? The first thing that I need in that expression for the confidence interval. Well, as you might expect, there's a function R called mean. So if I type mean parentheses x, and parentheses, there's my sample mean. Something else I'm going to need is quantiles from the t-distribution. Excuse me. So I can do, there's a function R called QT. We saw Q norm before. Well, QT for quantile t-distribution. And the corresponding probabilities, that 1 minus alpha divided by 2. I'm going to use the symmetry property. Well, let me just do this first. 0.975, the degrees of freedom is n minus 1, or 9. There's my first quantile. But since we know that the t-distribution is symmetric, I need both a positive and negative quantile. How about, again, I take advantage of how R does its calculations using vectors, and now I get the negative value, and I get the positive value as well. So I have 0.025 and the 0.975 quantile. I'm also going to need my standard deviation, so I'm going to use the SD function to do that. And a nice way to find the sample size, even though I already told you it's 10, is to use the length function. That's the length of the vector. Okay, let's start putting all this stuff together. So mean of x plus quantile from the t-distribution, times that standard deviation, divided by the square root of my sample size. And I get my confidence interval back. Make sure I got that right. Yep, good. So notice two values are returned to you. So again, this is going to be a good illustration of how R does its calculations. You know, I didn't need to do the lower bound first and then do the upper bound of that confidence interval. I was able to do it all at the same time by taking advantage of how R does its calculations on vectors. So let's take a closer look here. So this QT function, remember how that gave us two values back? What happens when I multiply it by the standard deviation of x? Well, the way that R reacts, because standard deviation of x is just one number, it takes that number times the first element that you get from QT, and then times the second element that you get from QT, so that in the end, you get two numbers back. Then look what happens then when I divide by the square root of that sample size. Again, obviously the square root of the sample size is one number, but I had two numbers over here after doing the t-distribution thing and the standard deviation thing. It applies that division to both of those numbers from the QT function, essentially. And then lastly, take a look at the mean here. That's one number, but everything on the right side gives you two numbers. What does it do? It adds that one number to both elements. And so that's how you're able to do all these calculations rather quickly. But of course, you know, this just means, though, you have to be careful. You have to understand how R is approaching this. So you don't have an unintended side effect happening. Okay. Now, there also happens to be a function in R called t-test, which will give you exactly the same result. So, t-test, the first argument says, where's your data? And they just happen to call the argument x. And it just so happens I have my data stored in a vector called x. Okay? Just a coincidence. Then it's actually set up to do hypothesis tests. So obviously I'm not doing a hypothesis test here, so I can put anything in for that second argument. Let's call mu, which is mu. Let's say mu equal 2. And then, well, what confidence level do I want to use then for a confidence interval? Well, conf.level is the argument name. Let's say 0.95. And here is the 95% confidence interval coming back to it. Okay. Are there any questions? Okay, unfortunately, we are out of time. We will continue talking about R. Next, yes?
So when you do those options in the parentheses? Do we have like specify that mu is equal to this value rather than like putting this?
Well, let's see if I had to actually specify something. I don't remember off the top of my head. So I can look up the help for t.test. So I could find it in a similar manner as before. T.test is in the stats package. Another way to find help that's actually quicker, and it is in the notes but I failed to mention it, is help.ttest. So I can just simply issue the command or the function help. Okay? And so if I come here, I see what the default is. It would have used mu equals 0 if I hadn't specified it. So I wouldn't have to actually put anything in there for mu. I think it would be confusing then to look at the hypothesis test results if you didn't know what mu was, even if we weren't even doing a hypothesis test here, which we're not. And so that's why I included it. So it's important, at this stage, what we're doing here is not necessarily complex, but it's important at this stage that you understand the terminology, such as what is an object, what is a function, what is the corresponding thing called arguments, what does it mean, how you have certain arguments you have to specify, and some that you don't have to because they have default values. And how to create a function as well. Those are the important things to get at this time. What we will talk about next time, one of the main things will be, let's say you want to put all these lines of code together into a program, like what can be done with SAS. What can you do? Well, we're going to write a program then. And there's a number of different editors that you can use to do this. As you might expect, since R is free, there's a lot of free editors out there. If some of you have heard of RStudio, that's probably the most used editor out there. It's not my personal favorite. I have other favorites out there that I will mention to you. And then, once we start doing those programs, then we can start doing a lot more interesting things. So that's it for today.